I joined the Tepper faculty in the fall of 2004 as a member of the information systems faculty. Prior to that, I spent 5.5 years or so at a company called FreeMarkets, which was based in downtown Pittsburgh. And we were one of the early online auction companies for business-to-business procurement auctions or reverse auctions. And while I was at FreeMarkets, my primary role there was to be the lead architect or the head architect in charge of our electronic marketplace products. I learned a lot anyways about how to make a software system effective. That was one of the biggest, hardest challenges. So from an academic perspective, you tend to think in terms of how do you specify very carefully what a set of software will do? How do you determine if the software is going to meet those requirements? How do you evaluate whether a design is likely to, say, perform at a given level, handle a certain number of transactions, have a certain number of bugs per 10,000 lines of code? These are all different types of metrics you might use in an academic setting. What I found when I was actually building them in FreeMarkets was there's an earlier step, and that's how do you build the right product to solve your customer's problem? That's especially tricky because your customer doesn't necessarily know what their problem is to start with. They know what they think they need, right? And they know that they have a problem, but what they think they need may not necessarily be the thing that solves the problem. That's a little bit subtle, but it turns out that coming up with a way to actually build a great system that will solve their problem, that is, that their employees can use, that the other people, their partners can use, that is reliable and robust, that actually changes the business processes or provides a new way of doing business so that the company can really take advantage of that and actually change how they do things instead of just doing things the way they did a little bit more efficiently. Those seem to be the really important precursors to building a great product or providing a great service. And so the jump from sort of a more formal, rigorous academic way of specifying software or evaluating what the needs were to getting down to the trenches and actually having to figure out what the real problem the customer was facing and come up with innovative ways to address those. Understanding the importance of that step was one of the biggest lessons. It turns out that's one of the trickiest things to do. And it's something that in many cases a lot of people from an academic or research perspective have trouble even addressing that because it's sort of the fuzzy front end or the soft and squishy part of it, not the rigorous scientific approach. Well, the first one is you need to talk to the customers. And that may sound obvious, but it's actually very difficult to do in some cases, or very difficult for many people to remember, that they need to actually go out and not just talk to the customers, but listen to the customers. Right? So it's a very different type of fishing expedition when you go out and tell the customers what you've built and why they should buy it, than it is to go out and talk to the customers and listen carefully to what it is they say they need, and also come up with techniques to observe them doing what they're doing so that you can find ways to help them do it better. It's fairly straightforward to figure out the requirements that are well known, the ones that your customers can articulate. It's a lot harder to figure out what we call the latent requirements, the requirements that are underneath the obvious answers that they provide. How do you do that? Well, one, you bring in your own expertise in building these types of systems and working with other customers. Right? So as you work with customers who face similar problems, frequently you can bring what you've learned working with another customer to bear on the problem that you're facing here. So that's one of the ways. Second way is you simply watch what they're doing. Okay? So you actually spend time working with them, watching what they do and how they do it, instead of just having them tell you what it is that they're doing. One is that you need to spend time with the customers. Another is you need to figure out what you actually can do. You need to work with the technology team. There are people who are going to build it to understand what's possible. You need to iterate. So one of the biggest lessons that we took away from that is that even if we really observed what they were doing very carefully, and even if we built the greatest thing that we thought we could, we wouldn't get it right the first time. We wouldn't get it right the second time. We wouldn't get it right the third time. And this is the role of iteration. So many of the more popular software development processes, techniques, etc., are geared towards how can you iterate quickly? How can you be agile in your processes? How can you recognize that the likelihood that an organization, either on the customer side who's requesting or speccing the technology, or the provider side, the people who are building it, the likelihood they're going to get everything right the first time is very low. So many of the new technologies and these are process technologies or approaches to designing and building software, are very iterative in nature. They recognize that simply coming up with a large specification document, throwing it over the wall, so to speak, having another team build it, is not an effective way to get useful software, to really solve problems with the software you're building. Many of the new techniques focus on frequent iteration. Throw something out, try it, see what happens, learn what worked well, learn what didn't work well, and then very quickly iterate and try it again. We see many of the, this is a technique that many of the more successful internet companies, the Amazon.coms, the eBays, the Googles, have really perfected. They can put software out for their user base. They put it out in beta. The use of beta has greatly increased over the last few years, largely for that reason. They can put it out to a select subset of their user base, get very quick feedback on what works, what is effective, what features are frequently used, what features are not frequently used, and then modify that and get a new version out as quickly as they can. So a lot of the new techniques that focus on rapid iteration, agile development, really frequent prototyping. Prototype more than once. Put a prototype out, see how it works, put another prototype out, put another prototype out, then maybe go and build the full version of it. Some of the most important lessons that I took away are the need to tie management goals, business goals, and technical goals. So if those three are aligned, then IT and your software development organization or your product development organization, again, depending on whether you are a company that's building and selling technology or a company that's using technology, when those goals are aligned in a way that's useful and sensible and strategic, then you can get a whole lot of benefit out of your investment in your software or your IT infrastructure. When the goals diverge, to a certain extent, it doesn't matter how good your business strategy is, and it doesn't matter how good your technical development capabilities are. If the business goals are divergent from the technical goals, you know, you're diverging, but it turns out you're heading for a train wreck. They seem to come around and hit each other anyway. So getting your business goals and your technical goals in alignment, understanding what your technical limitations and capabilities really are. So a business strategy that's not business strategy related to IT or product development that's not tightly tied to what you can do, what the technologies can do, is unlikely to be successful. A good example of this would be a product that we built called QuickSource. So our original real-time auction system that we built at FreeMarkets was based on client-server technology. That is sort of a precursor to internet-based systems. We didn't run it through a web browser, for example. Over time, we realized that our corporate customers were getting much more comfortable in doing things over the internet. Previously, one of the main reasons we'd done a client-server system instead of the internet is that our corporate customers were simply not comfortable conducting business over the internet. They did not feel that security and availability and other capabilities of the internet were there yet. They weren't willing to trust them. Over time, they did, however, trust them. So with our what we called Bidware, which was our real-time bidding system, we decided that sometime in probably mid-1999 that our customers were now ready for an internet-based system. So we had to change our technology strategy so that we were building internet-based systems instead of client-server-based systems that did very similar things. But that proved to be a very effective strategy for a variety of reasons. For one reason, the capital markets were greatly rewarding companies who had internet technologies versus client-server technologies. But completely independent of that, our intention was to grow very, very quickly and to be able to support many, many more customers than we were currently supporting. It means a lot of different things to a lot of different people, unfortunately. We haven't really, as a community or as an industry, come to a single firm definition of what software architecture or enterprise architecture is. As a general rule, the architecture of a software system or of an enterprise system consists of the major components of the system, the description of the connections between those systems, and the design rules or invariants that are used and enforced in building that system. So that's sort of the academic perspective of what an architecture is. In a more practical perspective of what a software architecture is, generally what you're talking about are the core elements of your systems and the ways that they interact and the rules that are used to support the interaction of those elements. Now this turns out to be a very, very important aspect, getting the software architecture right or the enterprise architecture of a big information system right tends to be a very, very critical aspect of the overall success. It tends to be very critical to the overall success of a systems deployment project or the general success of an IT initiative at a corporation. And the main reason for that is that many of your fundamental decisions are embedded in your architecture. So if you get it right, and getting it right is a tricky concept because it really means, and the process of architecting or the act of architecting is really just an exercise in making a series of decisions. And the trick is to decide what decisions you have to make, what decisions you can defer, and what order you need to make them. And the reason that that's important is because every one of those decisions you make limits the subsequent decisions that you can make. I think there's a handful of drivers for that. One is that architecture has emerged as a core standard part of the discipline. It's no longer seen as a fringe idea. It's no longer a novel concept. It's now fully integrated into the mainstream. So that's one of the main implications. A second main implication is we're just trying to build a lot of bigger, more complex systems these days than we were 5 or 10 years ago. The number of systems that are built that have millions of lines of code now is much larger than that number of systems that were that complex some large number of years ago. One of the main ways we're able to do that is by reusing different elements, different components. So instead of writing your own database, you now reuse an off-the-shelf database. Instead of writing your own user interface widgets, that is the controls that give you menus and windows, etc., you buy an off-the-shelf system and you hook them together. When you start putting a lot more emphasis on hooking components together rather than building the components yourself, the architectural issues become very obvious. It turns out that this user interface widget set that you bought doesn't actually work with this database that you bought. And the reason that they don't is that there's a connection mismatch. That there are assumptions that both of those elements make about the environment they work in, and the other component doesn't make the same set of assumptions. So that's one of the reasons that it's become more prominent, is that people are doing a lot more composition in making software than they used to. Another reason is that software is just a lot more obviously prevalent in people's lives than it was 5 or 10 years ago. With the growth of the internet, with the number of Americans that are people throughout the world, I guess, that now have broadband in their home and use it on a daily basis, the number of different electronic devices, cell phones, personal digital assistants, laptops, Xboxes that people use, all of those are driven by software. And in order to make that software work, there are literally millions of lines of code that are driving those systems. When you have that many systems that are that big, that interact as much as they do, so your cell phone, for example, now can hook up through Bluetooth to your computer so that they can exchange contact information or phone number information. Right? Those are the types of interactions that need to be enabled at an architectural level, by and large, to work effectively. One of the rules that I use when I'm talking about architecture is that there is no such thing as a good architecture or a bad architecture in and of itself. Architectures are good and bad in that they are either fit to purpose, that is, they meet the requirements and the architectural drivers that underlie a system, or they don't. So a good architecture is one that provides the level of performance that's required, provides the level of security that's required, supports the ability to build the features that are required, provides the level of availability or robustness that's required, provides the level of modifiability that's required. The interesting thing about those 5 different aspects of an architecture I just ticked off is that in many cases, improving one hurts the other. And so the decisions that an architect needs to make, some of the main decisions that they need to make, or some of the earliest decisions they need to make, are figuring out how important each of those 5 different attributes are. And by the way, there's probably 15 or 20 different attributes that you would typically work with as an architect. Those ones seem to come up again: availability, performance, security, modifiability, robustness. These come up again and again. So by understanding the requirements or the needs of the specific system that you're trying to build, you're more able to answer the questions of, should I be willing to trade off performance now for future modifiability? Should I be willing to trade off time to market right now for future modifiability or for security? And only when you understand those types of, or understand what we call the architectural drivers, can you decide whether your architecture is good or bad? And it's really not whether it's good or bad, it's will it meet the needs that we have for this system. Google has taken a process that is the deployment and testing of new systems or new features within their systems. They have cut the time that an operation of their size would require to do that by at least an order of magnitude from what is typical. So many of their new features, they have actually architected their systems in such a way that when they want to very quickly and iteratively try out a new feature, they can put that on their machines in a way that will not affect most of the other capabilities that they have, in a way that they can turn it off and roll it back if it turns out that it doesn't work properly or if it breaks something in a matter of moments, and in a way that they can distribute it across literally thousands of machines very, very quickly and very transparently to the user base. That is, I type www.google.com into my browser one time and it will take me to a screen that doesn't show me that feature. The next time I type it, it may show me the feature. And if I see it and 100,000 other people see it and we go and use it and it starts breaking their other systems, they'll be able to detect that very quickly, roll it back, and the next time I type in www.google.com, it will be gone. In order to do that effectively, you really need to architect the system from the beginning for rapid iteration, for experimentation, and for the ability to fix things if they break quickly. When you consider the scale, where they have tens of thousands of different servers that are running these programs distributed all around the world, it's really quite amazing to me that they've been able to do that in a time period that most companies trying to put systems onto their servers and make them available to their customers with a high degree of assurance that they will work. The rate at which Google can do that is just extraordinary. One of the first things that you need to do if you're trying to figure out what IT system should I build and how should I build it is this IT system going to help the overall strategy of the business? It doesn't need to be a huge strategic system in and of itself, but it needs to mesh with the overall business strategy. It needs to support business strategies. It needs to, sometimes it will enable new business strategies. We talked earlier about companies that took a very defensive posture. There are also companies that successfully take a very aggressive posture. That Amazon.com would be a strong example of this. These are companies that say, we are going to be able to build IT systems or products that are better than our competitors, that are going to enable us to do business in new ways that our competitors can't do business. And furthermore, by being ahead of the curve with the technology, we are going to gain other types of advantage. We're going to gain loyal customers, we're going to be profitable. We're going to pull ahead of our competitors in a way that may not be sustainable forever, but will give us an opportunity to build other types of barriers. The Amazon.com example I gave earlier, they've been very, very innovative over the years in how they apply IT. So initially they created an online storefront, much as many other companies did, but then they augmented it. They said, this is interesting. Now that we have all this data about who is buying what, we can put in recommendation systems. We can, so when you go to Amazon, you get something that you don't get by walking into a Barnes & Noble or a Borders actual physical store. Sure, you can't look through the books the way you can at those stores, but when you go to a Barnes & Noble bricks and mortar store, you can't really get opinions from the last 50 people who've read the book on whether they think that it's a good book, get a summary of them, etc. So that's one example of how they built innovative new IT systems that helped the general business strategy, that helped give them an edge over their competitors. Amazon did that 4, 5, 6, 7 times in a row. It was really quite impressive. That money, in each case, they were building fairly innovative capabilities. They were investing heavily in the IT, but they got very good return on it because they were able to make sure that what they were doing was aligned with the overall business strategy. A couple additional reasons why systems development efforts tend to fail. One is simply the phenomenon of trying something too ambitious. Right? Instead of saying, no, we can't do that up front, and being very realistic about what is capable within a given time period with a given set of people who have to actually go and implement it, trying to do too much. So instead of doing a smaller amount and being fairly aggressive in paring the scope of the project down to a point where the team that you have can, in a straightforward with a high likelihood implement and deploy the system in the time that you have scheduled for it, in the budget that you have set aside for it. Instead, many companies say, it's just software, how hard could it be? Let's just add features. Let's just add features. And frequently those features are added late in the game, right? So you may well have initially scoped the project to something that was manageable, but there's a great temptation as time goes on to say, oh, can we add this one to that release? Can we add this feature to the release? Wouldn't it be neat if the system also did this? A very disciplined approach to saying that will be available in the next release, that's great, we can consider that for the next release, is one of the best defenses for a development manager to actually get the system out on time. So scoping it properly, not being overly ambitious, and resisting the urge to allow scope creep to set in are some of the best ways to deal with the overly ambitious project syndrome. Additional reason that projects have a tendency to fail is simply poor risk management. So risk management is an easy thing to do in terms of, it can be very challenging, but a few simple risk management techniques applied judiciously through the project can greatly increase the likelihood of success. One of the most important things to do there is simply identifying what the biggest risks are at the outset of the project. Most projects, for most software development and implementation projects, don't go perfectly smoothly. There are bumps along the road. There are risks that were frequently identifiable at the beginning of the project that turn into actual problems as the project moves along. A simple exercise early in the project of identifying the key risks and developing contingency plans for what to do when those risks turn into real problems is one of the best ways to keep a project on track and also to help you keep the scope of it manageable. Understanding that some of these risks are likely to come to pass and you're going to have to deal with them will force you to build in a certain degree of buffer time to deal with the inevitable hiccups and speed bumps that happen on your path to completing your project.